right. So we discussed quite a bit about the various types of biases that can arise in the use of machine learning. There can be several biases that can arrive during even defining the objective function. You could have certain problems where your objective function is not very well defined. The machine learning can use proxy solutions or shortcut solutions to it is solving the objective, but it's not solving it in a desirable manner, right? So you could have various problems arising due to that. You could have various biases in data collection. You could have various type of other problems during your training, like privacy leakage and so on. And you could have various other types of issues when you are deploying the model itself, right? So we stopped here when we were discussing these feedback loops. So what is feedback loops is it is some type of uh, loop that occurs, or let's say a vicious cycle that occurs. So you deployed something, it had certain unintended consequences that you didn't imagine. And those unintended consequences lead to some changes in the data distribution, lead to certain other changes. And now that changed data distribution with the unintended consequences feeds into your machine learning system. So maybe the machine learning systems get even worse. It exacerbates the biases. And then again, it leads to these bad outcomes in the world, huge distribution shift. Then again, it feeds. It can create a vicious cycle, right? And we looked at this example of a feedback loop in a recommendation system. In a recommendation system, if you predict something that will be liked by the customer, even though you showed some very slight preference for that thing, right? You just maybe randomly click something, but now the system thinks that this person really likes this stuff and keeps on showing you the same thing. And now you might actually click it more than you are clicking some other content. And it might think, okay, this person is still clicking the content that I'm actually recommending, so I should recommend even more, right? So we will see examples of these type of scenarios as well. So just to summarize, there could be biases, problems in all sort of stages of the machine learning pipeline, and we have to be very, very careful. So here is a bit of I don't know if you can see this. It's a slightly smaller font. But this is roughly the taxonomy of human-centered AI approaches, what all are the type of approaches that we can adopt. And let's zoom in a bit. So the upper part is what we call as forward approaches. So the forward approaches roughly are that you incorporate more feedback from humans, right? Get more explicit feedback from humans about whether the system, whether the AI is using some shortcut solution, it's bypassing the objective or not, or is it aligned with human values or not, right? You do this sort of an alignment using additional human feedback. For example, a very popular thing in LLM training is actually the fine-tuning step, where you collect additional feedback from humans and you collect basically pairwise feedback. You might have experienced yourself when you're using ChatGPT, sometimes ask, do you like response 1? Do you like response 2? Right? And sometimes you say that response 1 is better, and now it's taking that into account and giving you responses of that sort. So this is the step where you are actually collecting explicit feedback from humans and ensuring that your model is not toxic, it's not abusive, and so on. So there's a huge layer of the safety training that's done, for example, on LLMs and so on, that incorporates human feedback. You can also do something which is during the training step, which is called robust training, where this is more useful in examples where you can have out of distribution samples, right? So for example, if you're making a self-driving car and you are supposed to stop on a stop sign, but the stop sign has some graffiti on top of it, your algorithm might actually not detect that that it is a stop sign, might detect something else, right? Because it didn't see that type of a graffiti on a stop sign in the training sample, right? So you should incorporate some sort of a robust training that the model should be robust to these type of out of distribution or adversarial examples and so on. And if you are concerned about privacy or fairness and so on, you can add these as constraints to your training objective as well itself, right? So these are some of the forward approaches which are done during the training step or the design step, right? There are other set of approaches which we call backward evaluation. So these are like post-training guidelines where you are trying to do some sort of a safety evaluation on the model. Okay, so there's things called red teaming, where what you do is you try to give adversarial questions to, let's say, to the LLM to see how it is responding, right? So, for example, there's a huge red teaming effort for safety of LLMs as well, where you are trying to ask what is like, can you give me some information about financial fraud? Can you give me some information about this, that, which is not supposed to, it is not supposed to give. And can you add some suffixes? Can you add some prefixes? Change the information certain way so that it gives you that information, right? So you don't want the user to actually be such that the user is so persistent. No, please give me this information. I'm speaking from authority and so on, and give you the information that it's not supposed to give, right? Because I'm I'm not sure how you are, but if ChatGPT is denying me an answer, I won't stop at one step, right? I will ask further. Okay, please give me. I'm speaking from authority. This is for research purposes only, right? Um, you can also include some sort of interpretability and explainability to your model so that it's doing some intended things. So you can try to understand which features are the most important features that the model is using and so on. And you can also do some sort of a privacy certification or fairness certification, and some sort of audits. So this is more useful in the regulatory framework. For example, if the government or some agency which is tasked to certifying the safety of the AI model, if it wants to run some audits, how should we do that? And the thing is that a lot of the models are actually proprietary models. They are black box models. So we don't have access to the data that they are trained on. We don't have access to the model weights itself. The only thing that we have is input and output, right? Given an input, what is the output it's giving? With that input and output information, can you actually certify whether the model is safe or not? It's following all the privacy guidelines, all the different other law guidelines and so on. Okay. So this is the rough taxonomy of what are the different sort of approaches or the different things that you should take care of when you're designing AI application, particularly in a human-centered manner. Today I plan to cover one specific um, aspect. Okay. So this was basically from yesterday, day for yesterday's lecture. Today, what we'll look at is one specific application and look at the all possible pitfalls that can arise in this application. Okay. So, particularly recommendation systems. So, this is also very close to my research area, and this is also something which has been in use for a long time, right? So people say that, of course, these days LLMs are very popular and so on, but they are more recent. The sort of I'm not saying that uh, there has not been work, but the buzz in LLMs is sort of recent. Recommendation systems are actually one AI that's been in mass huge usage for a very, very long time. Okay. So in early 2000s, even people were actually using recommendation systems for filtering content for their platform. For example, Amazon was using and Netflix and so on, right? Facebook from the very beginning is using recommendation system for variety of purposes. So the goal of recommendation system in general is to understand your preferences, understand user preferences. We did talk about it a bit in last class, and filter content based on your preferences, right? So since the content is huge, there is huge number of videos, huge number of items that you can purchase on e-commerce. We want to somehow filter the ones that are better or more aligned with your interests, right? And they are very, very useful in that manner because as Susan, as you go on YouTube, you see some recommended content and so on. And you don't have to particularly search which is the content that like. I like to watch this type of video, and so on. You don't have to search most of the time. Most of the time on the landing page itself, you can see their content. And oftentimes, if you are like looking at some video, it might also recommend things that are similar to that video. So that's also done by using a recommendation system. And there are various goals that are used for recommendation system training. So one is to enhance the user experience, make it more useful to the user. Oftentimes, there are also sales and engagement targets, right? You don't want to oftentimes push the items that are truly interesting to the user. You want to push the items that are more expensive, particularly when you talk about e-commerce or these days quick commerce, right? And so there is some sort of misalignment between these goals of satisfying the user most and the business objectives of the company, right? And it can lead to various type of problems. So in this lecture, we will look at some of the problems that could arise and discuss some of the phenomena that you actually see in practice and try to explain that why it happens. So this work in recommendation system actually got a huge boost through this Netflix prize. Okay, how many of you have heard about this Netflix prize? Perhaps you guys wouldn't have been born at that time. So I think around 2004, this Netflix launched this Netflix prize. So it is like a old ancestor of Kaggle. And here the goal was to develop a recommendation system for Netflix. So it released data about user and the rating that they've provided on the movies that they've watched. And now you have to predict the rating for new movies and new users. And with that, if you can predict, then you can actually, whenever a new movie is released or a movie that's not watched by the user, based on the predicted rating, you can sort, right? So this was hugely popular and a lot of teams participated in it. And people started working on this data quite a bit, and it became very popular. And you can see this contains a 1 million prize. So Netflix was willing to give out 1 million for just improving the recommendation system. Okay. Now, as you can see that ChatGPT has not gotten good enough. So it's not 1.000, it's actually 1 million. So it's instead of a comma, there should be instead of a comma, it's giving a dot. Anyways, so basically, you can see the importance of these Netflix of these recommendation systems. They add lots and lots of value to the platform because a lot of times improving the recommendation system, improving the user experience means a lot of revenue, additional revenue for the platform. Okay, and long-term engagement or long-term satisfaction of the users. Okay. I can I'll give you very nice examples as we go along of why this is important. But let's first look at the general paradigm. Okay. So this is just to get you started of on how we actually build a recommendation system, or how roughly most recommendation systems work. So what you try to do is you try to estimate these quantities of interest. Uh, let's say probability of click given a user item pair, right? So given a user and an item, what is the probability that the user will click on this particular item, right? It could also be what is the expected rating that this person will give to this user item. For example, in the case of Netflix, it could be rating. It could also be watch time, like to what extent will the user watch this item. And in the case of, let's say, Instagram, it could be like what is the probability that this user will share this to their friends or direct message and so on. And in case of e-commerce, this could also be the probability of purchase, the probability of eventual purchase. What is the probability that the user will, after clicking and seeing and so on, the user will eventually purchase that item, right? You could also have expected revenue of the item and so on. So you can have many more things here. And what you do is once you estimate this, so you can develop a neural network, a model that takes as input a user, an item embedding, and predicts the final probability of click, probability of whatever, and then assign a weight score to each of these, right? So you can assign a weight W1 to the probability of click. You can assign a weight W2 to the probability to the expected rating and so on. And for each item, you can calculate this score. So given a user for each item, you calculate this average score and rank the items based on this average score. Is this clear? Is this general thing clear? Like, yes, that's a very good question. So the weights are defined by the application designer based on intuition. You could also learn the weights. And there comes a very interesting story. So in 2016, Facebook suddenly decided to do this meaningful engagement thing, where it was just a fancy name for just saying we will change these weights. Okay, the way they changed these weights, they introduced additional buttons. So initially, before I think 2016-15, there was only like button that on Facebook. After that, they introduced angry and I don't know. Can you guys might know. What are the other? Happy, joyful, I don't know. So certain emojis. Have you guys used Facebook, or is it too old? Too old. Okay. So anyways, so think of Instagram over there. Like everyone, I think everyone has different reactions. Okay. So what Facebook decided is that we will do different weights for different types of reactions. Okay. So for like, there is one weight. So probability of like given this content, there's one weight. Probability of angry given this content, probability of joyful given this content. And somehow they gave angry 5 times the weight as like. Okay. And this was hard coded. So this was completely hard coded. Angry has much more weight than like or joyful or whatever. So what does that mean? What? More content which you don't like. More content that you're angry towards, right? So it would push the content that you're more likely to be angry higher, right? And what does that mean? It is likely to be political content. Okay, so around the 2016 election in the US, that was the time when they decided to do this. And what it just meant was that your angry uncle and aunties used to fight on Facebook. And around 2016 election, because that's the content that you get angry about, that this person did this ideology group did this and so on, and you are just sort of angry about it. those are the things that are pushed to you, and as a result, um, a lot of young people left at that time, and that was the time that I think they have not been able to recover. So since then, it's a lot of young people have left. And on Instagram, they are very, very careful about this. There are specific buttons like you can suppress political content and so on. But that's a different story. So that could be a result of a lot of things.
There have been used like outrages on 26 levels, something like that.
Yeah, so we will see some examples of that. That could happen. We can talk about this. This is a long discussion that we are trying to have, and perhaps we don't have a time for that in the class. But it's really like we talked about engagement versus utility, and perhaps that type of item is very, very engaging, right? So that is the general idea. So is this clear? Okay, so we went off on a tangent a bit, but essentially the idea is that this is roughly the general paradigm of recommendation systems. You can read about recommendation systems. There are different types on different ways. How do you model? There are a lot of implementation details, but I just want to give you just this general paradigm. Okay. So in this class, we will mostly focus on different types of biases that could arise in recommendation system and why those type of situations can arise. We won't go into the design details of recommendation systems. Okay. So as I said, let's do a more of a deep dive on these feedback loops and why such feedback loops occur. Okay. So let's take a look at a simple example. So there are two content types. One is red content, one is blue content. Okay. So very, very simple example. Perhaps it represents reality, perhaps it doesn't. It's a hypothetical example. There's only red content and blue content. And consider a fixed user. So there's only either one user on the platform, or let's say multiple users, but the preferences of all the users are the same. Okay. So you can roughly treat them as a single user. Okay, so single user, two type of content, and you have, let's say, equal preferences for red and blue. So let's say you are sort of neutral about it. You like both red content and blue content, and so this is encapsulated by the probability of click given shown red and shown blue. Right? Where shown red and shown blue, you click with some probability lambda. That's your overall click rate. You could also have probability of purchase, rating, whatever. But here we're just focusing on clicks. And at each time, this simple recommender recommends only one item. Okay. So you just get one at each time you open the platform, you just get one item. That's it, right? And you choose to click on it or don't click on it. Then you come next day, again, one item is shown and so on. Very, very simple setting just for us to understand this. So what happens is that for t is equal to 1 to up to whatever time horizon, the user arrives at that time, each time, or some user from the set of users, homogeneous users arrive, and you recommend items based on past clicks. Okay. So PT is the ratio of RT and NT. RT is the total number of clicks on red content before time t. Okay, reasonable. So total number of clicks on red that have been there, and NT is the total number of clicks in the past. Okay, so NT is total number of clicks. RT is the fraction of number of clicks on red content. So then, what is the natural recommendation strategy? Anyone? That's good. So you could have a deterministic recommender. If PT is greater than half, you could show red, or if PT is less than half, you're just trying to make one prediction, right? Binary prediction out, right? Or you could have a randomized policy also. You can show with, you can draw a like a Bernoulli random variable with probability PT. That's also fine. So in this case, we are doing that. We're drawing a Bernoulli random variable with probability PT. And we are showing red, that turns to heads, and showing blue if it. So the probability that you show red at time t is PT, and the probability that you show blue at time t is 193. Okay. So now let's say you have bootstrapped your new recommendation system based on some legacy system. Okay. So there was some legacy system in place which was not using machine learning. Now you want to include this new type of a thing. And in this legacy system, there were, let's say, alpha clicks on red and beta clicks on blue. Does that make sense? So at time t equal to 1, there were previously alpha clicks on red and beta clicks on blue. So at t1, it's alpha over alpha by 2, alpha plus 2. Okay, so the probability at time t1 is alpha over alpha plus beta, and then based on how you're getting clicks, you. So what is going to happen in this? Any predictions? So the question is, what would PT converge to as time t tends to infinity? Any guesses? You understand what's happening, right? You calculate the fraction of clicks. So let's say you are you are using the platform. You see how many times this user has clicked on this content, how many times this user has clicked on this content, and I will recommend with probability of these with probability equal to the fraction of the clicks. So what should this converge to? Remember that the preferences are equal, right? So equal preference for red and equal preference for blue. Any guesses? Yeah. What? 1. You're saying 1, it will converge to 1. Why is that? Okay. So you're saying that the red percentage will go up over time. Do people agree with that? The red percentage will go up over time. Unstable.
We start at if the user clicks on their
So you're saying that it will be biased towards the initial configuration. Is that what you say? Perhaps. Okay. So how many votes for bias towards initial configuration? How many votes for half? You can watch with half. No votes. Okay. So perhaps the right answer is this. Okay. So this is related to a nice sort of thing that is studied in probability theory, which is called Polya's urn. So in Polya's urn is a simple model. You have a urn which has alpha red balls and beta blue balls. And for t is equal to 1 to t, what you do is you draw a ball uniformly at random from the urn. Okay. And once you draw that ball, you see the color of that ball. You return that ball to the urn back, but you add one more ball of the same. Does that make sense? Is the model clear? You draw a ball, see the color, add the ball that you drew, and then add one more ball of the same color. Okay. And PT here is the fraction of red balls over the total fraction. Okay. NT here is sort of fixed, it's alpha plus beta plus t minus 1. Okay, because you started with alpha red, beta blue, and each time you are actually adding one more. So, can anyone see the connection between this and the recommender? Okay. So, for what value of lambda is this the same? Or is it always the same? Is this the same model? What? Which one? Lambda was the probability of click. So what value of lambda is this the same? Lambda is equal to 1, right? For lambda is equal to 1, this is the same as the recommender model. Because let's say you are clicking each time, and once you click, the next time the number of clicks on red has increased by 1. So the fraction, the ratio with which you pull is also, in this case pull, or in that case you recommend, is going to update by 1, right? So it's the same. But if lambda is something less than 1, it is called as sometimes called as slow Polya or whatever, like you are just skipping some steps. But the distribution is not going to change. Okay, so convergence is not going to change. So it is sort of well studied that this under Polya's theorem, the PT, the probability of or the fraction of red balls will converge to beta of alpha comma beta. Does anyone know what beta distribution is? No idea. So beta distribution is a distribution between that takes values that basically between 0 and 1, right? It's a continuous distribution. And the parameters are alpha and beta. So you can see for alpha and beta, so when alpha is 2 and beta is 8, you get this very large bias. So you will converge to some value here, right? And when beta is, when alpha is 8, so you have larger fraction of red balls, right? And lower fraction of blue balls. I think the coloring is messed up. This should be red color and this should be blue color. Fine. So if you start with the initial configuration of let's say 8:2, so 8 clicks on red initially and 2 clicks on blue, you will converge to a very skewed distribution that's roughly like the mode is like 0.9. And if you start at half, you will converge to a more symmetric looking thing. But this is a very biased thing. Does that make sense? So initial configuration matters a lot, perhaps, and it might just be a result of a random chance, for example, right? It might be just that you saw red content initially and just you happen to click on it for a few times, and that few times might just skew your distribution completely towards 1, right? Does that make sense? That might explain some of the feedback loops that we encounter in practice, actually. Okay. So this sort of phenomena actually is very explanative of some of the things that perhaps you were talking about, that once we click on something, we see more and more of that content. Okay. There is real world recommendation systems are of course very, very complicated, and this is not the entire explanation, but this can be one part of the configuration. Okay. So in our case of recommendation, we saw that in small bias in initial configuration can lead to large bias. Okay. So now what is the problem? Can anyone detect the problem, or can we choose a different recommendation strategy to not have this problem, right? Remember that preferences are the same. If preferences are different, then perhaps we can do something else. But here preferences are the same. So ideally we should show with probability half, right? So what should we do? Or what were we doing wrong in this case? Is that Any response? It's your time to be. It's your time to speak up. Basically, any answer is a good answer. Don't worry about it.
Initially, the problem was that when the finding outcome was depending on the initial steps, initial choices are basically much. So rather than having the number of people that divided by equal number of clients, as the probability of showing right, what we can do is we can put some number n and say n plus number of clicks on that divided by 2n plus the number of clicks is the probability we show right. So that would not put a lot of weight to the initial choice.
Okay. So essentially, you want to do this sometimes called random exploration, or you don't want to. You want to put away. You want to like roughly. You want to start with half. Right. That's your idea. Okay, that's a good suggestion. We can or we can do some false exploration in the start. It could like these are similar in some sense. We could say that till 10 or 20 steps, I would go with probability half, then I'll see what happens later on. Or you could add something like this, right? Like add to alpha, you can add some large value, and to beta also you can. We're adding some sort of trying to mitigate this original power. So that's one strategy. But there is actually something which is very important here that is slightly difficult to see, and it's difficult to see for platform designers sometimes, right? People who are designing the platform. So the thing is that the probability that the click on red is not equal to the probability that of click given you are shown red. Okay. So given that you see red, the probability of click is the same. That's the hypothesis, right? That's what we are saying, that the user has equal preferences, and given that it has seen red, we are just it will click at the same rate. But we are not taking into account in the historical data how many times red was shown and how many times blue was shown. Okay. If we take into account that, perhaps in historical data, the recommendation policy that was there only showed red, and that's why you have more clicks on red. And if you can correct for that, if you can do this estimation that how many times you actually showed this thing and how many times it was clicked, and based on that you decide the ratio, perhaps that would be a better. Does that make sense? Not clear? It's clear? Okay. So essentially, what's happening is that sometimes sometimes this might be possible that you know whether the item was shown to the user or not, but sometimes let's say the legacy system didn't even log that, right? The legacy system might just be storing some aggregate statistics that this is the number of clicks I had on this number of clicks. It was not storing perhaps more detailed information that each time what was the recommended items, what was the clicked items, and so on, right? So the idea is that in some sense it's also related to fairness in some sense, that you can have these biases because let's say one group didn't even have the exposure or didn't even have the opportunity to be exposed. It could be like in this case to be exposed to the user, or in other case it could be like exposed to education, exposed to certain thing, and so on. And one group had like huge exposure to these things. So in this case, perhaps like the blue had a lot of exposure to the user. That's why more clicks. And then, but you don't know this variable whether it was exposed or not, right? And if you just look at the aggregate outcome, right, the clicks, not the conditional outcome, you can have problems like this. Okay. So is this type of bias clear? That if you don't know the exposure level, right? And you don't account for that, you can have bias in your estimation. And you should be very, very careful in thinking about when you are actually yourself application designers, this type of bias should not creep in. Okay, so what if now in a recommendation system, what if your preferences change? What could happen? So here the preferences were the same always. So we never had this preference. What if I'm showing you more and more red content or more and more blue content, your preferences shift towards that, you start liking that content? What can happen? So you can show that if there is the user is shifting along with the algorithm, then in the previous model there is no hope, right? It will just converge to one. Okay. But in real scenarios, this does happen. Like people do tend to change their preferences. To what extent is not clear. If even today, recommender systems don't have good models for behavior of users. I'm saying this because I have actually worked on real world recommendation systems, and this is just a very challenging task to actually simulate a human and how human preferences shift over time. So typically people don't actually model that. And the only thing is to keep retraining as soon as you think that you have not retrained for the past time. So, okay. So now this is good. This is something which perhaps can be solved if you knew whether the user has been shown the item or not. Okay. Now let's look at something which is very, very hard to actually fix. Okay. So this is something that a lot of current recommenders are not able to handle because this type of data is not there. So what I'm talking about is position bias. Now you're recommending 10 items instead of just one item. And naturally, there will be some ordering over these items. Okay. Now, you are showing all the 10 items, but you're not telling me which position I'm showing the 10 items, right? So the exposure is very, very hard to find out. So let's say you are Netflix and you are showing this in a slate, you're showing movies in a slate. You don't know which movies the user has maximum attention to. Or if you are like, let's say Google search or something, you don't know which are the maximum exposed items of the user. So the top items will naturally get more clicks. Does that make sense? And the bottom items would not get as many clicks. And if you again just do this estimation based on like whether the content was shown to the user or not, probability of click given shown, you would have this type of a position bias that things that were on the top position, right, will be actually accessed much more by the user and hence more clicks on that. So there will be a bias based on the position. And it's very hard to account for it because you don't know how the user, for example, particularly for Netflix, it's not clear. At least for list-wise, people have done a lot of cognitive analysis that people tend to start from the top to the bottom, and top positions have much more fraction of clicks or attention from the user. But on a Netflix type thing, it's not clear whether you're starting from the right to the left or from the left to the right or from the middle and so on, right? So you can have position bias like this. If you can assume that the bias or this attention is not dependent on the item, it's just dependent on the position, then perhaps there is more chance to fix it because you can find the probability or the differences in exposure and you can account for those things. But if it also depends on the item itself, then it's very, very hard because you don't know what is the position item exposure. Does this make sense? Okay. So there is lots of research on this, recent research as well. If you're interested, definitely talk to me. I also teach this in my class about how to fix position bias. Okay. This position bias is also related to something called popularity bias. So popularity bias is again when you have some items which are very popular item, let's say, and they're always shown in top positions. You get more data on them. You have better estimates of your probability of clicks on them, right? The items which are sort of niche items, you get like very low clicks on them, very little data. Your models are not very good on those items. And as a result, what happens is that this popularity bias also gets reinforced over time. Okay? So you get some items which are just very popular, and you get much higher click rate for them, and so on. So it's slightly related to position bias as well, because the items that are top in the position typically are the popular items. And so these two go hand in hand. I have do a lot of research on, I'm actually conducting a lot of research on popularity bias and how to fix that and so on. The other type of bias is, of course, cognitive bias. And cognitive bias is basically what we saw in the last class as well. This is some of the example that I started with. So if you have content which is like very clickable, right, almost like clickbaity, right, and this is some of the examples that the gentleman there brought about. So if you have some things that which are like very click worthy, or you just have this instant tendency to click, you will basically click them. So it is basically like a system one thing, and you will basically not act according to your system two, which is your true likelihood footprint. Okay, and it can also be like how the content is presented. It could also be that maybe the content is sort of actually very informative, but maybe there is it's just not presented in the right manner. There's no good thumbnails or whatever. So all those issues are there, and a lot of times what happens is that only system one preferences, which are this instant clicking tendency, gets into the system or gets taken up by the model, and a lot of system two preferences are actually brushed down under the carpet. So I presented this, and I have some research on handling this type of cognitive bias and thinking about long-term recommendation systems as well. Please, this is both a lecture and a advertisement of my research, by the way. So just to so essentially, like we can handle these type of biases to some extent by doing the upweighting and downweighting. For example, if you have some signals which are more related to system two, like some sort of explicit signals. Okay? So things like sending messages to your friends, right? That might be a, like, let's say you see a reel and you send it to your friends, and like that's a signal that you actually really like that content. So there might be things you just scroll and so on, and maybe like or click on like and so on. But if you're explicitly taking action of sharing it to your friend, you can see that as a more explicit signal. So the idea is to use more explicit signals, which are actually from system two as compared to system one, and rely less or give less weightage to more implicit signals, such as just scrolling or liking and so on. Right? And you might have seen that Instagram is, I think, very sensitive to this type of thing. Like if you're sending reels to your friend, you could most likely go off. It could also be like they are also asking this interested, not interested. If you have seen it on Instagram, that's another attempt at collecting more explicit signals. Because if you're explicitly clicking at interested, not interested, you are actually doing. You are only doing it because you want to inform the system about your preferences. This is not just an implicit thing that you just click randomly. Right? So you can upweight these more explicit signals and downweight these more implicit signals and correct for some of these biases. So with that, I would like to end. And there are lots and lots of examples of such biases. And if you see recommendation systems as a whole, it has many these types of biases like these, and many things that you need to think about when you're designing a system like that. If you can now think about LLM. So LLMs is like recommendation systems times 10. Because it has not only the ability to recommend, it has the ability to interact with you, very interactive. And some of these things, some of these biases are definitely also present in recommendation in LLMs and other future technology or AI, AGI, whatever will come. Okay, so lot to think about and research on, and thanks for your attention.